Hello, everyone, and a very warm welcome to Kognito Key. I'm so thrilled you're joining me today. We're going to dive right in, because today we are exploring the absolute fundamental building blocks of modern electronics. We're talking about PN junctions, and specifically, the magic of forward versus reverse biasing. Now, have you ever wondered how a single, tiny electronic component, literally just a little piece of silicone, can magically switch between allowing a massive flow of electricity and then completely blocking it? It feels a little bit like magic, doesn't it? But actually, it's just brilliant, beautiful physics. And the secret to this whole switching behavior lies in a really simple process called biasing.
Part 1. The basics of biasing and applying external voltage.
So, what exactly does biasing mean? Well, biasing is simply applying an external potential or voltage to our device. By supplying this external power, like from a battery, we're basically manipulating the internal positive charges, which we call holes, and the negative charges, the electrons. We are essentially giving them a set of instructions on exactly how to behave inside that silicon. Moving on to part 2, forward biasing, or what we can think of as the closed switch. Let's break down exactly how this works. In forward biasing, we connect the P region of our device directly to the positive terminal of a battery and the N region to the negative terminal. Now think back to basic Coulomb's law. Like charges repel each other, right? So the positive battery terminal actively pushes the positive holes away, and the negative terminal pushes the negative electrons. This strong repulsive force shoves all those majority carriers straight across the junction. It shrinks that neutral barrier in the middle, which we call the depletion width. Because they overcome that barrier potential, you get a high, sharp flow of current. Just like that, the device is acting as a perfect conductor. Next up, part 3, reverse biasing, the open switch. Okay, but what happens if we just flip that battery around? Let's say we connected the P region to the negative terminal and the N region to the positive terminal. Well, because opposite charges attract, the positive holes get pulled toward the negative terminal, moving far away from the center. And the electrons, they get pulled away too, straight towards the positive terminal. Because both are pulling away from the junction, that middle barrier, the depletion width, thickens up drastically. This restricts almost all of the majority current flow. You're left with just a very tiny, minor leakage current caused by minority carriers. So it's effectively blocking the electricity altogether. Part 4. Comparing the key differences. A tale of two states. Let's put both of these concepts side by side. The entire difference here boils down to one simple physical connection: how the positive and negative terminals of the battery are wired to the P and N regions. P to positive and N to negative gives us forward bias, but P to negative and N to positive gives us reverse bias. It really is that straightforward. Looking at these states like this gives us a fantastic way to grasp the differences instantly. Just look at the depletion width. It goes from super thin in forward bias to really thick in reverse bias. And because of that, the resistance shifts from very low to very high. Consequently, the magnitude of current drops from a high flow down to just a tiny low leakage. Ultimately, forward bias creates a low-resistance conductor operating exactly like a closed switch. Reverse bias, on the other hand, creates a high-resistance insulator, acting as an open switch. So you might be asking, why does all of this actually matter in our daily lives? Let's connect the physics to some real-world applications. When engineers need devices that emit light or switch super quickly, they rely heavily on forward biasing. Think about the bright LEDs in your home, tunnel diodes, or Shockley diodes. On the flip side, reverse biasing is absolutely crucial when we need to safely regulate voltage or detect light. That is the exact foundation for Zener diodes, varactor diodes, and photodiodes. Literally, almost every single electronic device you use today relies on this clever little manipulation of physics. I truly hope this explainer made the concepts of forward and reverse biasing crystal clear and fascinating for you. It really leaves you wondering, doesn't it? If engineers can control the flow of electricity so precisely with just a simple piece of silicon, what other invisible forces in your daily life are being manipulated right under your nose? If this helped you understand PN junctions better, please make sure to subscribe to Kognito Key right now. Hit that like button and share this explainer with your friends and classmates. Thank you so much for learning with me today. Keep exploring, and I'll catch you in the next explainer.